Hello Wizzes, in this video I will be showing you how to find a normal force of a car moving on a hill and a roller coaster loop using centripetal forces. If that sounds interesting, let's hop into it. Now before we jump in, recall that the centripetal force is a type of net force that acts when objects move in a circle. So if we have an object here and it's moving with a tangential velocity v, and we have a net force acting at a 90-degree angle from the velocity, then what will happen is the object will begin to move in a circle. And the centripetal force Fc is a type of net force, and it's equal to the mass times the centripetal acceleration. And the centripetal acceleration is equal to the object's speed squared over r. Now, the reason we said v is the speed is because in uniform circular motion, the speed of the ball is always going to be the same, but it's always going to change direction because the upward force here is going to cause the rightward initial velocity to change direction. So the velocity is changing, but its speed remains the same. So v is the speed, and r is the radius of the circle in which the object moves in. And we also said that Fc is a type of net force. It's not a particular force acting on an object. So, for example, let's say we have a horizontal circle here, and let's say that the force pulling the ball in this circle is a tension. Let's say we have it on a table, and there's just a tension acting upward, causing the ball to move in a circle. So, the net force on the ball is just the tension, because the tension is the only force that acts on the ball. And because that tension is what causes the ball to move in a circle, we can set that equal to the centripetal force, which is equal to m times v squared divided by r. So keep in mind, the centripetal force is not a particular force. It is a net force or a sum of forces that act on an object. So how can we apply centripetal forces when a car is moving on top of a hill and at the bottom of a hill at its highest and lowest points with the rightward velocity? So these are two different cases. Let's start with the case where the car is at the top of a hill. So the question we should ask ourselves first is, what forces act on the block? So obviously the earth is interacting with the block, so we must have a downward gravity force equal to mg acting on the block. And the surface below it must be exerting an upward normal force on the block as well, equal to Fn. So the net force on this block is equal to, well, first, what direction should be our positive acceleration direction? Is it going to be up or down? And we usually set our acceleration, the positive acceleration, to be in the direction of the net acceleration. So what direction is that going to be in? Well, we see that this block is eventually going to travel downward in this diagonal direction. So it will have a diagonal velocity like this of v. So if the velocity changes from going to the right to going to the right and down, then we have a downward net change in the velocity, which means that at the top here, the acceleration must be downward. So our positive acceleration is going to be downward. And our net force in case 1 at the top is equal to mg minus the normal force. So mg is greater than Fn in the first case. Now, if we have a circle here, we can actually imagine this half of the hill here to be this half of the circle. So we can just pretend that this block is here, and we have a rightward velocity v, and our net force is acting downward. So can we call F net the centripetal force? Yes, we can. So we can change F net to be, recall, it's mv squared over r, and we can set that equal to mg minus Fn. So that's the equation we're going to be using for the top of the hill right here. Now, what about at the bottom? What happens at the bottom? Again, we still have two forces acting at the bottom of the hill here. We have a downward gravity force equal to mg, and we also have an upward normal force equal to Fn. And this time, the net force, the question is, which one's bigger? We see that kind of like the last example, except this time, the block is eventually going to move with upward right diagonal velocity. So that implies that we need to have an upward acceleration at this point in order for that to be possible. So we're going to take upward to be our positive direction in this case, and the net force will be equal to Fn minus the downward gravity force. And once again, if we imagine our circle, and here's our block, the block should be at the bottom actually. So if we imagine our circle again, then we can just pretend, oh, here's our rightward velocity, and our net force is pointing upward because Fn is greater than mg. Fn greater than mg. And once again, we can set this equal to the centripetal force. So that means we can say that the net force is equal to mv squared over r, once again, case number 2. And it's equal to Fn minus mg. So for case number 2, where you have the car at the bottom of a hill, this is the equation we're going to be using. So save these two equations. So number 1 is for the top, and number 2 is at the bottom of the hill. And we're going to do a couple examples to examine how these forces exactly work. So here's a practice problem, and if you'd like to try on your own first, you can pause the video, but I will be doing this problem in the video too. So what we have here is a block moving on the same hill as before with a radius of 10 meters, and at both positions, the block has a velocity of 8 meters per second. And the question is, what is the normal force at the highest and lowest points of the hill? And what is the maximum speed the car can travel at the top without flying off the hill? So how do we approach this? So up here, we already have the equation for the normal force and net forces. So that's mv squared over r at the top for part A equal to mg minus Fn. So all we have to do here is solve for the normal force. So let's add Fn on both sides. So we end up with mg, I'm going to reverse the direction, is equal to mv squared over r plus Fn. And now we just need to subtract mv squared over r on both sides. And that gives us that Fn is equal to mg minus mv squared over r. So this is our equation for the normal force. So from here, all we have to do is plug in our knowns. So the normal force is equal to m, which is the mass is 50 kilograms, times gravitational acceleration, which is 9.8 meters per second squared, minus the mass, 50 kilograms, times the velocity, which is 8 meters per second, quantity squared, divided by the radius, 10 meters. So that's equal to, I'm going to omit units. If you multiply these out, that's 490 minus 320. And we get an answer of about 170 newtons for the normal force at the top. And notice how the normal force is less than the weight force here, which was 490, which means our assertion was correct. Now, what about for B? What is the normal force at the lowest point of the hill? Again, we already have our equation, which is mv squared over r is equal to Fn minus mg. So all we need to do to find a normal force is to get this term on its own. So all we need to do is add mg to both sides. That gives us Fn is equal to mg plus mv squared over r. Now, like before, all we have to do is substitute the values. So Fn is equal to 50 kilograms times 9.8 meters per second squared plus 50 kilograms times 8 meters per second squared divided by the radius 10 meters. And that gives us around 490 plus 320 when you put it in a calculator. And that gives us a normal force of about 810 newtons. So that's our answer here. Now what about part C? What is the maximum speed the car can travel at the top without flying off the hill? Now if you look at when the velocity was 8 meters per second, notice we have a normal force of 170 newtons. When we have a normal force, that means the object is on a surface, because in order for there to be a normal force, the object has to be on a surface. So if the car flies off the hill, then it's only subject to the gravity force. There's no more normal force. So the question here is, what is the largest value we can make this before Fn is equal to 0? Because when Fn is equal to 0, that's the minimum. If Fn is a negative number, that's not even possible. So we want to find for what velocity is Fn equal to 0. So let's try it out. So if the normal force is 0, that must be equal to mg minus mv squared over r. Let's add mv squared over r to both sides. So we get that mv squared over r must be equal to the gravity force mg. We have m on both sides, so we can cancel that. So we end up with v squared over r is equal to g. And multiplying both sides by r, we get that v squared is equal to rg. And if we take the square root of the whole equation, the maximum speed the car can travel is equal to the square root of the radius times gravitational acceleration. So the maximum velocity is equal to the square root of r times g, or 10 meters, times 9.8 meters per second squared. And that gives us about 9.899 meters per second. So at the top of the hill, the velocity must be less than or equal to 9.899 meters per second in order to stay on the track. Here, there is a maximum threshold. So we have a max threshold. So knowing how we did the hill problem, how can we figure out the centripetal force that acts on a block going around a circular loop? What is the centripetal force at the top of the roller coaster loop here? So let's analyze the forces that act on the block. So obviously gravity acts on the block downward, so that's equal to mg. And because the surface is up here, the normal force should also be pointing downward, perpendicular away from the surface. So it's gonna go downwards as well, Fn. So net force, we already said was equal to the centripetal force, because this block is gonna travel in a circle on this loop. So that means that, well, we should take downward to be our positive direction, because the net force and acceleration are going downward. So mv squared over r is equal to Fn plus mg. And the normal force, Fn, if we subtract by mg on both sides, we get that Fn is equal to mv squared over r minus the weight force mg. So what exactly does this equation imply? When we look back at the hill example where we had a block moving across the top of the hill, we said that the normal force was equal to mg minus mv squared over r. And we said that there's a maximum speed in which the car can travel before it flies off the track. And the car flies off of the hill or track when Fn is equal to 0. When we look at this example here, we can see that there's a certain value v has to be in order for the car to remain on the track. If the velocity is too low, then the car will just fall off before it reaches the top here. So v, there's a minimum value for v. And still we set the normal force equal to 0. So 0 equals mv squared over r minus mg. And if you do algebra like you did before, you'll end up with mv squared over r is equal to mg. And you can cross out m like before. And v is still rg. But in this case, v has to be greater than or equal to the square root of rg in order for the car to stay on the track. When you have a hill, v has to be less than or equal to the square root of rg in order to stay on the track. So let's try this problem. You can pause if you want to try on your own first, but what is the minimum speed that a car weighing 30 kilograms must travel on the top of the loop in order to remain on the track, given that the radius is 5 meters? So from before, when we have a car moving on top of a loop here, v must be greater than or equal to the square root of rg. And this is a minimum speed situation because if the block doesn't move fast enough, then it will fall off of the loop here. The force will not be enough to keep the block in circular motion. So v would be equal to, for the minimum speed, the square root of 5 meters times 9.8 meters per second. So v is equal to the square root of 49, or 7 meters per second. So this is the minimum speed that the car must travel to remain on the track. Also notice how the mass of the car is irrelevant to the car's minimum speed that it has to travel. It's only based on the radius of the loop. Now let's try a slightly different problem. How can we find the speed of the car given its normal force and its mass and the radius of the loop? So we're trying to find the velocity of the car at the top here. So once again, the net force is equal to mv squared over r, and that's equal to the sum of Fn plus mg. They act in the same direction. Now this equation would be really ugly to solve for v, so the best thing to do here would just be to plug in the numbers. So m is 30 kilograms times v squared, which is the unknown, and the radius is 5 meters, and that's equal to normal force we said was 500 newtons, and mg is equal to 30 times 9.8. So for simplifying this a little bit, we get that this here is 6 v squared, and that's equal to 500 plus 30 times 9.8. And if you add this together, you'll get a value of 794. 30 times 9.8 is 294. So 6v squared is equal to 794. And now we can just divide by 6. V squared is equal to, this quantity here is around 132.333. And if you take the square root of that, we get that the velocity of the car is equal to 11.503 meters per second. And that's our answer. Thanks everyone for watching my video, and if you have any questions, feel free to put them in the comment section below. Have an amazing day, stay happy, and we'll see you next time. Goodbye.